In this video, we're going to look at redox and half equations, and this is really just an introduction of what you should already have an idea about from GCSE, because you're going to do a lot more about redox at A level. So, as we said, redox reactions are going to be important in a range of different contexts at A level, and you should know some basic definitions for how we can determine whether something is oxidation or reduction. So we've got oxidation as being a gain of oxygen, and we can see that in a really simple example of elements like magnesium reacting with oxygen in the air, which is also a combustion reaction. Follows then that reduction, being always the opposite of the oxidation, would be the loss of oxygen from a compound, and we've seen that in maybe metal reactions, extraction from ores. At A level, actually, the gain of oxygen and loss of oxygen is really going to be mainly concentrated on in an organic chemistry context. And the other thing that we will talk about in organic chemistry is that hydrogen being gained is actually reduction, and loss of hydrogen is oxidation. So they are the other way round. Hydrogen and oxygen have different effects when they bond to atoms. But really what we want to concentrate when we're thinking about half equations, particularly at the start, is our definition of oxidation being the loss of electrons from something and reduction being the gain of electrons. And you may have used the mnemonic oil rig. Oxidation is loss, reduction is gain. So it's important to realise that this doesn't apply to oxygen because it's the opposite way round. It applies to electrons and hydrogen, but we're not going to come across that much. The other thing to realise is, of course, electrons can't just disappear into nowhere, and they can't appear out of nowhere, which means that if we're writing a full equation or an ionic equation, which is still a sort of full reaction happening, then the amount of electrons lost is going to be equal to the amount of electrons gained. So you need to be able to identify redox reactions, and in the last video on reaction types I actually gave you a clue on how you could identify them. So here are 5 reactions. Try pausing the video now and see if you can decide which of these are redox reactions and which are not. Okay, are you ready to check your answers? Reactions 2, 3 and 4 are all redox reactions. The way that we can spot this really easily without working out anything to do with electrons or charges or anything else is the mere fact that each of these reactions involves some sort of element on one side of the equation and a different element on the other. In fact, these all 3 are counted as displacement reactions because in all of them a element is being displaced from a compound by a more reactive element. And so the reason that we know that this must mean that redox is happening, for example, if we look at magnesium, magnesium on its own has no charge, but when magnesium becomes magnesium sulfate, an ionic compound, magnesium becomes Mg2+. And there is a similar situation happening in the other 3 reactions. So the other 2 equations, the first one is a neutralization reaction, and reaction 5 is a decomposition reaction. So as you go further through the course, you're going to learn a lot more about chemical bonding and oxidation states, and then it will become a lot clearer why reactions 1 and 5 are not redox, and it will also become a little bit clearer as to why these displacement reactions are redox, and also you'll be able to identify more complicated redox reactions, but that's all you need to be able to do for now. And you need to be able to write some ionic and half equations for redox. So remember that ionic equations do not contain spectator ions. And previously we might have considered a spectator ion as being something that didn't change state, like in precipitation, something that stayed in solution. For the context of redox at the moment, a spectator ion will not change its charge. So, for example, sulfate stays as SO42- on both sides of the equation. It doesn't turn into SO2 or any other species involving sulfur. So we're going to look at two examples because you don't need to do difficult ones at the start, and they're both going to be displacement reactions. Hopefully you remember a little bit about displacement reaction. It's when a more reactive element takes the place of a less reactive element in a compound. And you should have seen two examples of this, one with metals and one with halogens. So here's an example of a simple metal displacement reaction between magnesium and copper sulfate. The magnesium is more reactive and is displacing the copper from copper sulfate. So what does that mean in terms of redox? It means that magnesium is undergoing a chemical change because it starts as magnesium metal, which we're just going to write as Mg. Remember, we don't need to turn everything into an ion to write an ionic equation. If it's just Mg on its own, we'll leave it as Mg on its own. But on the other side of the equation, the magnesium is part of magnesium sulfate, which means since our sulfate ion has a 2- charge and magnesium's in group 2, magnesium has a 2+ charge. That means that magnesium is losing electrons, and we'll look at that in more detail when we do the half equations. Copper is undergoing the exact opposite change. So it starts as Cu2+. It's a transition metal, so we might not necessarily know off the top of our heads that copper has a 2+ charge, but we can tell because of the formula with copper sulfate, CuSO4. And then it forms just plain copper on the other side. So there is an ionic equation for a simple metal displacement. There's no balancing to do, and the reason there's no balancing to do is because the two metals have the same charge, 2+, so the same number of electrons is lost and gained. Here's a second displacement reaction. So this is involving halogens, the displacement of bromine from potassium bromide by the more reactive halogen, chlorine. So in this one, the chlorine is starting as an uncharged diatomic element, and we're still going to write it in the same way. So we don't split up the two chlorines in Cl2 in the ionic equation because they are still covalently bonded together in the same way that we wouldn't sort of split up H2O or anything else in an ionic equation. We only remove spectator ions. In this case, it's the sodium that's not doing anything. The sodium is in a compound on both sides, so it is +1 on both sides of my equation. Chlorine is going from Cl2 to Cl- in NaCl. The normal charge on a chloride ion, -1. There are two of them because there were two chlorines in Cl2. So remember, we don't remove the balancing numbers, we are only removing the sodiums from this equation. That means that bromine has basically undergone the exact opposite process, started as bromide ions and became bromine molecules. Notice how specific the language is I've been using to describe these particles. So in this reaction, bromide ions, Br-, react with chlorine molecules, Cl2, to make chloride ions and bromine molecules. This use of language is even more important at A-level than it was at GCSE. We can see though with halogens that if we look at the other two possible displacement reactions that could happen with iodide being displaced by chlorine or iodide being displaced by bromine, like precipitation reactions, the ionic equations are really repetitive. So the only thing that changes is the element symbols. All the balancing is the same, all the charges are the same. Okay, finally we're going to look at half equations, and we are really only going to look at slightly more simple examples here because they will get a little bit more complex later in the course. Half equations, like ionic equations, so they're even more they've They show even less, but they definitely do not contain spectator ions. And because of the name, half equation, they're going to show either the oxidation process or the reduction process. So either the loss of electrons or the gain of electrons. Just like any other symbol equation we've come across, the atoms are still balanced, the charges must still be balanced, and in fact we balance the charges often with electrons because we're showing electrons lost or gained. So half equations are the only equations where we are allowed to include electrons, and we only show them on one side at a time. So let's use our example of magnesium and copper. We've already written an ionic equation to show the displacement reaction. How are we going to turn this into two half equations? Well, first of all, I'm going to split up the magnesium and the copper processes. So magnesium on its own turning to Mg2+, and copper 2+ turning to copper. So we've separated it into two halves with the two different elements that are involved in the reaction. Let's have a look at what magnesium is like at the start of the reaction and what it is at the end, because this way is hopefully reasonably obvious to tell where the electrons are going, but let's see why we put the electrons on the side that we do, just using dot and cross. So magnesium has the electron arrangement of 2 and then 8 and 2. So that's what Mg is going to look like. Whereas when we draw a magnesium ion, we remove that outer shell of 2 electrons and we have an electronic configuration of just 2, 8, and that's where my 2+ charge comes from. We're all quite confident at writing those at GCSE. And then that means that we have 2 electrons left over. So we're going to show that in the half equation as being on the right hand side. You can see that it needs to be on the right in order for there to be the same number of crosses, the same number of electrons on each side of this equation. We started with 12 electrons around the magnesium, we ended with 10, so there are 2 left over. Those are being lost. So the electrons are no longer part of the magnesium, which means electrons are lost, meaning it's oxidation. Oxidation is loss of electrons. I'm not going to draw the electron arrangement of copper because it's a transition metal, but you can see exactly the same thing must happen in the opposite way round, that a copper 2+ ion must have to gain 2 electrons to become copper. So hopefully the metal one, not too complicated. How do we do it with the halogens? So let's look at how we'd apply this to a halogen displacement reaction and make half equations for that. So here's my ionic equation for bromide ions reacting with chlorine molecules to make chloride ions and bromine. As before, we're going to take the two halves of the reaction. So there's the bromine half and the chlorine half. And we're going to write them separately with the reactants and products on the correct sides. Let's have a look at what happens, and I'm going to use chlorine as my example to see what happens with the electrons. Now I'm only going to show the outer shell because it'll take a little while otherwise with chlorine because it has 17 electrons per atom. Outer shell is the only thing that changes, so that's all we need to do. Chlorine's in group 7, so the reason that we've got this diatomic molecule here is because we've got this electron arrangement with each chloride ion having 7 electrons, sharing one single covalent bond to make Cl2. And then on the other side of the reaction, each of those chlorine atoms are now separate from each other. So we have here got 7 electrons each. Now that's not possible, we can't just have 7 electrons like that, and so what's happened is we must have gained 2 electrons in order to produce 2 chloride ions. So if I was going to balance it, I'd have to write those 2 electrons on the left hand side, so that if we just added everything up, all the dots and crosses, there would be 2 lots of 7 for the chlorine, add 2, so that's 14 plus 2 is 16. And on the right hand side, because I've got 2 ions with their negative charges, they've got 2 lots of 8, so that is also 16 electrons. So I'm just making sure that my electrons haven't sort of disappeared out of nowhere. So electrons go on the left hand side because that's where they need to be to balance the equation. The other way of looking at it, of course, is that now the charges are balanced, so there are 2 minuses on each side. That means that chlorine, I've had to add those electrons on. Each chlorine has gained an electron, so that process is reduction. Another way to spot reduction in a half equation is that the electrons are on the left hand side of the equation, and in this case in oxidation the bromine is undergoing exactly the opposite change from an ion to an uncharged compound, and the electrons are on the right hand side. Half equations are useful because we can consider separate oxidation and reduction and use them to work out a full balanced equation. But what we can also do is, if we know 2 different half equations and we are given them, even if they're not familiar, we can work out the full equation by balancing out the electrons. So this is a familiar half equation, we've just written it, bromide ions going to bromine. And then the second half equation is something that I'm going to guess you've never seen before, because I just pulled it out of a book. So this is difluorine oxide reacting with hydrogen ions, and it's being reduced by gaining electrons, they're on the left hand side, and it's forming 2 fluoride ions and water. So never seen that reaction before, but we do know that if I was trying to combine these into a reaction between bromide and F2O, then the only thing I've got to make sure when I write an ionic equation is that there are no electrons. At the moment, if I simply added these together, it wouldn't work. And that's because the top equation has 2 electrons lost, and the second equation has 4 electrons gained. You can't lose 2 electrons from one equation and then gain 4 from another. The electrons don't cancel each other out. If you connected that in a circuit, the electrons would have to flow around. The same amount would have to be gained at one end of the circuit as were lost at the other. So what do? We treat it like a simultaneous equation in maths where we're trying to get rid of and cancel out the electrons. So I'm going to rewrite the bromine one, because the bromine one is the one that does not have enough electrons at the moment. So if 2 bromide ions produce 2 moles of electrons, then if I have 4 bromide ions, I will make 2 bromines and 4 electrons. So what I've done is I've taken that whole top equation and I've times the whole lot by 2. Once I've done that, I can then add together my left hand side, my reactants, for both equations, keeping everything present. So if there are hydrogen ions in that equation, I'm going to leave them in. So I've got my F2O plus my 2H plus, I've used those up. 4 bromide ions of what it needs to react with. I've used that one up. My electrons cancelled out, so I'm just going to put them down here in brackets, so you can see they're on the left hand side. Nothing is left from the left, so I'm now moving over to the products on the right hand side, where I make 2 F minuses, 1 H2O. I've got from my bottom equation 2 Br2s and my 4 electrons, which are in brackets. They're not part of my full equation because the whole point is they have cancelled out. It's the same on both sides. I can check that everything adds up. So on the left hand side I have 2 pluses from my H plus and 4 minuses from my bromide, which gives me sort of a total of 2 minus. And on the right hand side I have 2 minuses from my 2F minus, which gives me a total of 2 minus. So that's fully balanced. Even though I'd never seen that equation before, all I've got to do is balance the electrons. You'll do more of that in the redox topic.